Hello from BASF. This webinar will give you an overview on the requirements for OLED emitters. The presentation will explain why we believe that iridium carbenes are the perfect emitters for organic light-emitting diodes. Before we start, let me illustrate the opportunities for OLED materials, especially emitter materials. Today, AMOLED displays are already a multi-billion-dollar market. The market is dominated by small and mid-sized displays being used in mobile applications. We are currently experiencing the dawn of OLED TV, which will lead to further market growth. According to recent market forecasts, which have been cited by OLED-Info, OLED materials sell for approximately $1 billion in 2015. In 2020, this will have grown to $5 billion, of which $1 billion is the share of emission materials only. Other studies promise an even more optimistic outlook. Therefore, it is valid to assume significant growth for phosphorescent emitter materials. In the past, the phosphorescent emitter material segment was tightly protected by base patents on phosphorescent OLEDs. When such base patents expire in 2018, additional market entry opportunities for alternative material suppliers, which own proprietary phosphorescent emitter technology, arise. It is common expectation that high-performance phosphorescent emitter materials can only be created from a few chemistries, for example, phenylpyridine or carbene type. In summary, we believe that proprietary phosphorescent emitter material is a keystone technology for material and system providers in the near future. Here is the outline for this webinar on advanced OLED emitter technology. The webinar will start with a basic comparison of different OLED emitter technologies. We will discuss application requirements for display and lighting. Then, a summary of suitable emitter chemistries will be presented. An update on recent developments of green and blue phosphorescent emitter materials concludes the webinar. Let's start off with a comparison of different emitter technologies for OLEDs. In the late 80s, Ching Tang and Stephen Van Slyke and the team at Kodak discovered electroluminescence from organic thin films. At that time, OLED technology was based on fluorescent materials due to the lack of other options. Device structures were comparably simple, as the OLED fabrication process was in its infancy. The schematic to the right indicates the fundamental process of electroluminescence in a fluorescent OLED. When electron-hole pairs recombine to form excitons, quantum mechanics rule that approximately 25% of excited states are so-called singlets. The remaining 75% of excited states are triplets. Singlets and triplets differ in what the scientists call spin configuration. In conventional fluorescent materials, these states do not mix. This means there is no exchange of energy between singlets and triplets. As a consequence, light emission is only observed for the rapid decay of singlet-excited states to the ground state. The probability of a radiative triplet state decay towards the ground state is negligible versus other non-radiative loss processes. An upper limit of 25% internal quantum efficiency is then often assumed for fluorescent OLEDs, meaning 75% of the input power is converted to heat. Defying these efficiency limitations, early OLED products were utilizing fluorescent emitter technology, often using fluorescent dyes which are doped into appropriate charge-transporting matrix materials. Fluorescent blue emitters are still state-of-the-art for today's lighting and display applications. But overall, the importance of fluorescent emitter technology is losing out in favor of phosphorescence as the industry has made the transition towards the use of red and green phosphorescent emitters. Phosphorescent OLEDs were first discovered by scientists from Princeton University and the University of Southern California. Since the late 1990s, this technology has developed to become the dominating OLED emitter technology on the market. Again, a schematic depicts the basic process of electroluminescence in a phosphorescent OLED. The most significant difference is that by incorporation of heavy metals into the emitter molecule, so-called spin-orbit coupling allows mixing of the singlet and triplet states. This mixing of singlet and triplet states leads, on the other hand, to extremely rapid transfer of all excited states into the triplet states. On the other hand, these triplet states can now relax into the singlet ground state while emitting light during that process. As a consequence, an internal quantum efficiency of 100% is viable and has been achieved for red, green, and blue phosphorescent emitters. As indicated before, red and green phosphorescent emitters have now replaced their fluorescent counterpart. For blue phosphorescent OLEDs, stability is still a challenge to be solved before fluorescent blue emitters can be replaced by phosphorescent ones. The most recent emitter concept was greatly matured by scientists from Kyushu University in Japan and is called thermally activated delayed fluorescence, or TADF for short. In the view graph on the left, only one important condition for TADF materials is indicated, namely a small gap between the singlet and triplet excited state. In reality, material design is mastered by a more complex structure-property relationship, which would exceed the scope and purpose of this webinar. Having a small singlet-triplet gap seems to be a prerequisite for reverse intersystem crossing. The latter term describes the transfer of energy from a triplet-excited state to a singlet-excited state. Plainly speaking, if I want to play tricks on quantum mechanics, one does not want to roll the exciton far uphill. The reverse intersystem crossing is considered to be a rather slow process, but can be engineered to a few microseconds. Once the energy is transferred via reverse ISC, the singlet-excited state undergoes a rapid decay, and light is emitted. Again, 100% internal quantum efficiency shall be expected. Yet, TADF does not have a commercial impact. A major challenge in the coming years is to demonstrate that TADF materials can fulfill color and stability requirements while being used in production OLED stacks. When this challenge is solved, TADF bears the promise as a second option to realize high-efficiency OLEDs for lighting and display. When comparing the commercial prospect of emitter materials based on fluorescence, phosphorescence, or TADF, it appears obvious that the foreseeable future belongs to phosphorescent emitter materials. In the remaining time, this webinar will focus on phosphorescent emitter technology. In lighting applications, light color is expressed by color temperature. Light quality is often associated with how perfect a light source can render colored objects. The image to the right shows CIE color coordinates for various color temperatures. Typical lighting systems exhibit color temperatures ranging from around 3000 Kelvin and above 4000 Kelvin. In the case of the lower temperatures, light is perceived as warm white, which is used by many people for residential lighting. Color temperatures of 4000 K and above are perceived as cold white and are often employed in office lighting systems. When it comes to light quality, OLEDs have an intrinsic advantage over inorganic LEDs. Two emission spectra are compared in the shown view graph for the same color temperature of 4000 Kelvin. The upper spectrum represents an inorganic white LED. In gallium nitride-based inorganic LEDs, blue light with a very narrow emission spectrum is generated. An inorganic phosphor then converts part of the blue light spectrum to yellow and red light. As a result, there is some lack of cyan to green color in the spectrum, which is reflected in only moderate color rendering index. The lower spectrum shows the characteristic of a typical white OLED for lighting, utilizing 3 distinct emitter molecules in the device. Emitter colors used in this example are blue, yellow, green, and red. Compared to the LED example above, a more uniform spectral power distribution is evident for the OLED spectrum, which is reflected in a higher color rendering index. Typical LED light sources exhibit a color rendering index of 80 or below, whereas OLED light sources exhibit color rendering index of 90 and even above. Now, how important is deep blue phosphorescence for lighting applications? All phosphorescent white OLEDs are needed to close the efficiency gap towards inorganic LEDs. Recent developments have yielded white OLED panels with approximately 140 lumens per watt. At the same time, color requirements play an important role in the commercialization of R&D results. The view graph to the right indicates color coordinates for typical red, yellow, and 3 alternative blue phosphorescent emitters. In lighting panels, the desired white color point is achieved by adjusting light emission from 3 primaries, red, yellow, and blue. It has to be pointed out that only those color coordinates can be achieved by mixing, which are lying within the triangles defined by combinations of red, yellow, and blue emitters. To meet lighting specifications, the deviation of a certain white color point from the indicated Planckian locus must be minimized. Now we compare a greenish-blue emitter with a CI-EY color coordinate of 0.4 to a deep blue emitter with a CI-EY color coordinate of 0.2. For the greenish-blue emitter, a color temperature of 4000 K would be outside of the possible color coordinates by mixing greenish-blue with red and yellow. Therefore, such blue emitters may only suit niche applications. In contrast, the deep blue emitter would allow any to achieve cold white color temperature of above 6500 K by mixing deep blue with red and yellow. Calculations confirm that a light blue phosphorescent emitter would satisfy color requirements for most lighting applications discussed today. When consumers judge on display quality, resolution, contrast ratio, and color gamut are among the most important factors. Regarding contrast ratio, OLEDs bear an inherent advantage over liquid crystal displays due to OLEDs being a self-emissive technology. Let us focus on the TV application, as this can be the main growth factor for OLED in the next few years. Most current TV sets offer an HD resolution of approximately 2000 pixel lines. Most HD TV sets specify a color gamut of close to or more than 100% sRGB color space. The view graph to the right indicates the color gamut of this sRGB color space. Today's top-of-the-line TV models often feature UHD TV resolution, which is also marketed as 4K TV. Here, 4K TV represents the approximate number of pixel lines, namely 4,000. Display makers have already showcased 8K TV demos, which can be assumed to be the future standard. Such a display comprises 7,860 by 4,320 pixels, or 4 times the pixel count of a 4K TV and 16 times the pixel count of an HD TV. While improving resolution standards, panel makers will also need to satisfy improved color standards to be successful in the market. Already next-generation 4K TVs are expected to meet advanced color requirements. The view graph now shows the wider NTSC color space compared to sRGB, which may be adopted for 4K TV sets. The most striking difference is found in the green color. In NTSC color space, the green color is much more saturated than for sRGB. Display experts predict that for 8K TVs, even further enhanced color gamut is required. You can see a comparison of the already discussed color gamuts and the color gamut requested by the International Telecommunication Union in Recommendation BT 2020. In the REC 2020 color specification, red, green, and blue color are extremely saturated, and the addressable color space is approximately 2 times larger than sRGB. The color coordinates of bottom-emitting red, green, and blue OLEDs are indicated as well. The blue square represents the color coordinate of a blue fluorescent OLED. All other dots indicate color coordinates of phosphorescent OLEDs. Although the emission color can still be tuned to more saturated emission, for instance by using top emission devices or color filters, the ultimate color target may only be achieved by constantly developing more advanced emitter materials. We believe chemistry is the key enabler for the OLED industry. So, then let us take a look at the chemistry. Obviously, the properties of emitter molecules are determined by the choice of emitter chemistry. 2 examples are shown at the bottom. In devices, the emitter chemistry has major impact on key properties, such as emission color, efficiency, and stability. If we now focus on emission color as one distinctive feature of an emitter molecule, we see that more than one chemistry is needed to cover emission colors in the whole visible spectrum. Phenyl-imidazoles-based emitters are reported to achieve light blue to orange-red color. Reports for derivates of iridium phenylpyridine range from cyan to deep red. BASF has access to several proprietary emitter chemistries, among which phenylcarbene and dibenzoquinoxylin are highlighted. Combined, the BASF emitter chemistry portfolio covers the whole visible spectrum from deep blue to deep red. We consider the iridium carbene emitters as a stronghold of BASF's OLED portfolio. For the next slides, let us focus on very recent results for highly stable green and blue OLEDs. BASF strongly focused on blue emitter development. As shown before, market requirements for green emitters are greatly advancing. We believe that iridium carbene chemistry has advantages over the existing green emitter chemistry in order to fulfill these requirements. Today, we are happy to present results for highly efficient and highly stable green emitters coming from our recently started Green OLED development program. Green emitters were developed with target CI-EY color coordinate of 0.58 to 0.64 to be used in TV, respectively, mobile applications. Color coordinates of 4 examples are shown in the CIE diagram to the right. BGE1 and BGE2 exhibit deeper green color, whereas BGE3 and BGE4 have lighter green color. The BASF green emitter portfolio is complemented by a yellow emitter BYE1 for lighting applications. The excellent performance of the light green emitter BGE4 is demonstrated to the right. The lifetime LT95 for an initial brightness of 5,000 nits is approximately 1,200 hours. We use a standard acceleration factor of 1.6 to derive a lifetime LT95 of more than 15,000 hours at 1,000 nits brightness. The very same device exhibits very high efficiency of 22% external quantum efficiency and achieves a brightness of 1,000 nits at a very low voltage of 3.1 volts. Now, the view graph to the right shows the BASF track record for performance improvement of green emitter technology since the BASF development program started. It was possible to develop a competitive green emitter based on iridium carbenes within less than 1 year. We expect further optimization potential for BGE4 itself and several follow-up candidates in the R&D pipeline. Highly stable proprietary host and exciton blocking materials have been developed to offer a complete green OLED solution. BASF green emitter materials, as well as corresponding blocking and host materials, are accessible in scaled quantities. Highly efficient and stable blue OLEDs are considered as the biggest challenge for OLED materials development. On the other hand, a solution for blue is a highly rewarding target. Among all approaches brought forward in the past, iridium-carbene complexes remain as most promising emitter class for highly efficient deep blue OLEDs. BASF has developed blue emitters for lighting and display applications. The target CI-EY color coordinates range from 0.30 for lighting to 0.15 and below for display application. Two examples are demonstrated. BBE1 was developed for display application and has a deep blue color coordinate of CI-EY equal to 0.17. It exhibits a very high external quantum efficiency of 18% and low driving voltage of 4.4 volts. Compared by initial performance, BBE1-based OLEDs outperform fluorescent blue OLEDs. The development must now be targeted to improve the current lifetime for deep blue phosphorescent OLEDs. BBE2 was developed with a light blue color coordinate to target lighting application. BBE2 achieves a high external quantum efficiency of 16% and a very low voltage of 3.9 volts at a brightness of 1000 nits. Compared by the given data, the lifetime of BBE2 is more than 4 times the lifetime of BBE1. In lifetime-optimized devices, BBE2 achieves nearly 1,000 hours of operational lifetime before degrading to 70% of initial brightness. This is within close reach to market entry requirements for full phosphorescent OLEDs. Let us conclude the webinar. Due to ever-advancing requirements, the display industry has a continuing need for advanced OLED materials. Especially new phosphorescent emitter materials will have a great impact on the overall success of AMOLED displays. Today, we demonstrated that our emitter materials fulfill AMOLED requirements already now and have great potential for further improvement leaps. We believe that the complete BASF OLED material and technology portfolio offers a unique opportunity for the rapidly advancing development of deep blue to deep red OLEDs. When this webinar raised your interest in phosphorescent emitter technology from BASF, do not hesitate to contact the BASF OLED team with any inquiries. Contact information is displayed at the bottom.